Okay.
Thank you all for coming today. It's my pleasure to introduce Nalin Fonseka, coming from University of Central Florida, presenting can a positive density dependent dispersal counteract an Allee effect?
Central Missouri, actually. That's okay.
Thank you.
It's all right. So, yeah, I just want to talk about part of a study that we did a few years back. Like this is, since this conference is geared more towards mathematical modeling, I want to talk about some mathematical modeling here. So this is a joint work with Cronin, Goddard, Leonard, and Shivaji. First, I want to give you an overview for my talk today. So I'll be going over the modeling framework a little bit here today, and then the model of interest. And next, I'm going to show you the main theorem that we can use to study similar models, similar differential equations. And then I'm going to show you some computational results. Finally, if I'll have time, I'll show you some stability results that we can prove for this particular model. To start with, here is the modeling framework. A population exhibiting a certain growth and density-dependent dispersal on the boundary can be modeled by an equation of this form. What this does is that this equation models the density of the population living inside this habitat omega star, which is surrounded by a hostile out exterior region. Okay, so in this model, this V is of course the population density. This alpha tilde of V is the probability of the population staying inside the domain upon reaching the boundary. And R is the patch intrinsic growth rate. You may have seen these types of models in your OD class where you have this intrinsic growth rate. And D is diffusion rate in the domain, and D naught is the diffusion rate in the matrix, and S naught is the death rate in the matrix. Matrix means this outside region, okay? In the habitat, this blue region is what I call the matrix. And then uh, what we are going to do is we are going to do some standard scaling for this problem to come up with a more convenient model. What we really do here is we try to write our original domain omega star as a scalar multiple of a fixed domain omega whose measure is 1 and it has the same geometry as the geometry of the original domain. Okay. In doing this domain scaling, we come up with this new model, the scaled model. Here, this L is the size of your original domain. If it is a two-dimensional domain, it's going to be the area. If it is three-dimensional, it's the volume, so on and so forth. Okay. So this is the model that you come up with if you do that standard scaling. As a result of that scaling, this domain size comes into the model. Okay. So now we can obtain the corresponding steady state model by plugging ut is equal to 0. Okay. So because in this, when it attains the steady states, ut is going to be 0. If you plug in ut is equal to 0. And at the same time, I'm going to use these substitutions. I'm going to take lambda to be this quantity and gamma to be this quantity, and g of u is defined by this quantity. By the way, here again, this alpha u is the probability of the population staying inside the domain when they reach the boundary. 1 minus alpha u is what we call the emigration probability. That means the probability of the population leaving your habitat, okay, when they reach the boundary, of course. And this is the corresponding steady state model, the very general version of the model that we study here. Again, this f of u is the growth of the population. Lambda is a parameter related to the size of your original domain. And g of u represents the emigration pattern. Okay, that is g of u depends on 1 minus alpha u, which is what we call the emigration probability. All right, now I want to show you the model of interest. In this talk, I want to focus on a one-dimensional model. As you can see, the one-dimensional version of this model is going to be this equation. Okay, this is the equation part, and these are the boundary conditions. I'm focusing on a unit domain here, 0 to 1. Okay, so the boundary conditions are specified at 0 and 1 in these two equations. And of course, I'm going to take my growth term to be this specific growth term. This kind of a growth term is called a weak Allee growth term. What that means is that uh, this function is increasing. The per capita growth rate, if you look at the per capita growth rate, that is increasing for smaller densities, and it starts decreasing for bigger densities. Okay, so again, this 1 minus alpha u is the dispersal probability. And depending on the shape of this 1 minus alpha u, we will get different immigration patterns on the bound. So we can study different density dependent immigration patterns on the boundary by changing this 1 minus alpha u. Of course, if 1 minus alpha u is a function of u, then we say that we have a density dependent immigration. If 1 minus alpha u is a constant, we say that we have a density independent dispersal on the boundary. Okay, it doesn't depend on the dispersal. I mean the population density. For this model, these are the cases that we studied. We consider these particular types of 5 different types of 1 minus alpha u, that is emigration probabilities. The first type is emigration probability is constant. The second type is emigration probability is increasing. We say that that's a positive density dependent immigration. And the next type is decreasing, that is negative density dependent immigration. The next type is U-shaped. The last type is M-shaped. So these are the types of immigration patterns that we studied for this model. Next, I want to state the main theorem that we proved for this model. And first of all, here is my model. I'll call that model 1. I want to give you a characterization of the solutions to this model. Remember, the positive solutions to this model are nothing but the positive steady states of your population. Okay. So if you take a positive steady states, typical positive density profile, or a solution to this equation, that solution looks like this. It's a concave down function like this. And I'm going to take T naught to be the point at which the maximum population density occurs. And I'm going to take the maximum population density to be rho. As you can see, this is a unit domain, see, 0 to 1. So this is the domain I'm in. And the population density at the left boundary, or at 0, is Q1. This height is Q1. Population density at the other boundary is Q2. Okay. With these quantities being introduced, I can state the first theorem, the main theorem. This model has a positive solution U such that the maximum of the solution is equal to rho, and U of 0 is equal to Q1, and U of 1 is equal to Q2, with Q1 and Q2 between 0 and rho, if and only if lambda rho Q1, Q2 satisfy these 3 equations. And in that case, T naught, this T naught value is given by this equation. Okay, so as you can see, since this is an if and only if statement, this gives you a kind of a complete characterization of the solutions to this equation. Okay, in particular for undergraduate students, this method will be a very interesting and very effective method for you to study any type of differential equation of this form. Okay, you can deal with different types of reaction terms and different types of boundary conditions. Okay, you can even derive this method for the directly boundary conditions case, in which you have U of 0 is equal to 0 in the boundary and U of 1 is equal to 0 in the boundary. Okay. All right. So the importance of this theorem is we can just focus on these 3 equations. If we can find lambda, rho, Q1, Q2 satisfying these 3 equations, we can go back and find a solution to this equation, because this is a if and only if statement, right? So that's the usefulness of this theorem. We will be always dealing with these 3 equations to get the solutions, the structure of solutions to this original problem. Of course, the solutions to the original problem will be positive steady states of your population. And here, by the way, here this uppercase F is the integration of this reaction term from 0 to S. Okay, this is called sometimes the primitive of your lowercase f, the primitive of this function. All right, now I want to give you an outline of the proof for the forward direction, and I'm going to leave the backward direction as an exercise, giving some hints for you to try if there are undergraduate students here. I'm going to take U to be a positive solution to this model. Then we need to show that this lambda rho Q1 and Q2 satisfy these 3 equations. So U is the positive. I'm taking U to be a positive solution with these characteristics. And then I'm going to multiply both sides of this equation by U prime. Since it is a positive solution to this equation, it should satisfy this equation. And then I'm going to multiply both sides by U prime. I get this equation. And then if you integrate both sides, you are going to come up with this particular equation with f is as defined before. It's the primitive of lowercase f. Um, from the chain rule, you can easily see that this is going to be your integral. And then you can find this integration constant c using the fact that u of t naught is equal to rho. Remember, at t naught, you have the maximum steady state size, right? So using that, you can find that constant c. And then plug in that back in here, you can solve for u prime of t. You are going to come up with two equations. Remember, you have a square here. When you take the square root, you get plus or minus. Plus means this region, right? In this region, your u is increasing. That means the derivative has to be positive. So for t between 0 and t naught, you get the plus case, and the t between t naught and 1, you get the negative case here. And then if you rearrange this equation and integrate both sides from 0 to x, x is between 0 and t naught, you get this equation. Integrating the second equation, you get this particular equation, okay? And now, if you use the substitution v is equal to u of s, you will get these two integrations. Okay, it's just a substitution, using a substitution to transform this integration to these two integrations. Okay, we are almost there. These are the two equations we have at the moment. Now I'm going to take the limit as x approaches to t naught. Remember, as x approaches to t naught, your u of t naught is rho, right? So the upper bound becomes q1 to rho here. The upper bound is rho. And in the right-hand side, you get t naught here. And here also, you get this equation if you take the limit. Now, if you add these two equations, you will immediately find the value of lambda. The lambda is given by this particular equation. And of course, these two equations can be proven by analyzing these two equations. Here, basically what you do is you plug in t is equal to 0 here, and then you use your boundary condition. See, u prime of 0 is gamma times the square root of lambda times g of u of 0 times u of 0. You can plug in it there. And if you do that, you can easily obtain these two equations. So the forward direction is done. Okay. And here is the activity for students. If there are students here, undergraduate students, you can show the backward direction using the implicit function theorem. So basically what you do is you assume that there are quantities lambda, rho, q1, q2 satisfying these equations, and then you need to show that there has to be a solution to the original differential equation. Okay, so you can prove that using the implicit function theorem. Next, I want to briefly show you how we obtain a relationship between lambda and rho, which is what we call the bifurcation diagram. Okay, so our ultimate goal is to use these three equations to get a relationship between lambda and rho. That is what we'll be using to make certain predictions about the population. Remember, lambda is the size of your original domain. It is, of course, related to the size of the original domain, but without loss of generality, we can say it's the size of the domain. And rho is the maximum population density size, okay? Okay, here is what we're going to do. We are going to divide this interval 0 to 1 into n equal subintervals, maybe n plus 1 equal subintervals. And then I'm going to pick my rho values in this interval. By the way, here when you have a reaction term like this, you can show that your maximum density size is less than 1. Since you have a positive Falling zero, unique positive Falling zero of 1 here, we can show that maximum of the solution is always less than 1. So that's why I'm focusing on this interval 0 to 1. So now what I'm going to do is I'm going to go over one by one. I'm going to pick these points one by one. For example, if I pick row 1, I'm going to go ahead and plug in that A1 to these two equations and use Mathematica or MATLAB to calculate, to find the value of Q1 and Q2. Once you have value of Q1 and Q2, and of course you have the value of rho, it is row 1, you plug in all these three quantities in this equation to find the value of lambda. That way, you have this lambda rho pair, right? You run this, you repeat this process for all I goes from 1 through n. So that will give you a pair of points, right? Set of pair of points, and those pairs can be used to generate the bifurcation diagram or a relationship between rho and lambda. Okay. So as I mentioned, this relationship can be used to make certain predictions about your population at the end of the day. Okay. So here is another activity. If there are students here, uh, try to prove that. Take your reaction term f of u to be this particular reaction term with a is equal to 0.5 and set your g of u to be 1. Just on the boundary you have g of u 1, and then try to get this relationship using Mathematica and show that you get a curve like this. So that is the second activity I wanted to give you. And then I want to briefly show you some computational results that we obtained here. These are not analytical results, of course. These are purely computational. Remember, this is my model again. Uh, I'm going to take, before I show you the results, I'm going to take the principal eigenvalue of this problem to be E1 gamma. Notice that this problem is nothing but the linearization of this problem about the zero solution. Okay, so you obtain this eigenvalue problem. I'm going to take E1 gamma to be the principal eigenvalue of this problem. Then it can be proven that E1 gamma is equal to this quantity. Okay, I'm going to leave this also as an activity for students. Uh, of course, what do you mean by a principal eigenvalue for this problem? That means the first positive value for which non-trivial solutions for this equation exist, right? So you should be able to show this using the ODE concepts. It doesn't require anything more than ODE. And then I want to show you some numerical results that we came up with. Typically, when you have a weak Allee growth term like this, your bifurcation diagram looks like this. Bifurcation diagram means the relationship between your domain size and the maximum size of the population looks like this. As you can see, it is going to the left initially from E1 and then turns back and goes to the right. Okay. So there are some interesting dynamics happening when you have a bifurcation diagram like this. I will talk about that in the last few minutes. But what we wanted to see is that even though we have a Allee effect growth term like this, can a certain density dependent immigration forms eliminate that Allee effect? Could we get a bifurcation diagram like this instead of a bifurcation diagram like this? Okay, because the dynamics of these two cases are going to be very different. So that's what we wanted to explore. By the way, here, a situation where this bifurcation diagram is going to the left of E1 like this initially is called an Allee effect. Okay, this length is called the Allee effect region length, whatever the length you get here. All right, this is what our study shows here. Uh, we studied all the 5 types of density-dependent immigration forms, as I mentioned earlier. Density-independent immigration, positive density-dependent immigration, negative U-shaped density-dependent immigration, and hump-shaped density-dependent immigration. And these are the prototypical types that we use for each immigration type. And what our studies show is that if you take this particular type of density-dependent immigration on the bound, the positive density-dependent immigration on the boundary, it turns out that we can kind of counteract this Allee effect. Okay, so what happens is that these are the immigration probabilities that we tried for in this case, 1 minus alpha u. As you can see, if you look at these blue curves, they are kind of a drastically increasing, right? Initially, they are drastically increasing, and these red curves are kind of increasing. They are also increasing, but not as fast as these blue uh, immigration probability curves, right? So these are the corresponding bifurcation curves for these immigration probabilities, these blue curves. These are the bifurcation curves. As you can see, those bifurcation curves are kind of immediately going to the right of the bifurcation point. Bifurcation point is this point E1. Okay, that's what we call the bifurcation point. And the red curves are going to the left initially and then turns back and goes to the right. What that tells you is that if you have a strong positive density dependent immigration, if your population exhibits a strong positive density dependent immigration on the boundary, then you don't get an Allee effect for that population. Okay? Your bifurcation diagram immediately turns to the right and goes to the right. And of course, this is for practical purposes. Okay, but theoretically, it might go a little bit to the left and then turns back and goes to the right. But that is very little. For practical purposes, it's almost counteracting an Allee effect. All right, here is the Allee effect region length on the M1 gamma plane. Remember, M1 is the parameter that we used in this particular positive density dependent emigration type that we have picked in this case. So if your gamma M1 is in this particular range, you don't get an Allee effect. And if your gamma and M1 in this white range, range 2, you are going to get an Allee effect. Okay, so that means these blue curves are corresponding to this white region. So that means if you have a strong positive density dependent dispersal on the boundary, you are always going to counteract the Allee effect. Okay. All right. So that means at the end of the day, if you use a strong positive density dependent emigration, you get a bifurcation diagram like this. Okay. All right. I will come back to this bifurcation diagram after I show you this stability results that we talked about here. Again, remember E1 is the principal eigenvalue of this eigenvalue problem. And remember the solutions to this problem, the model 1 is going to be the positive steady states of your population. Then we were able to show that the trivial solution of this model is asymptotically stable if lambda is smaller than E1 gamma, and it is unstable if lambda is bigger than E1 gamma. Okay, so what that tells you is that if you have a bifurcation diagram like this, bifurcation diagram means it's the relationship between lambda and rho. Suppose that relationship is like this. In that case, as I mentioned, if your bifurcation curve goes to the left initially, we say that we have an Allee effect there. When you have an Allee effect like this, some interesting dynamics are happening. So, for example, if your habitat size is bigger than this particular number E1, then doesn't matter how small your initial population is, your population is going to grow up and settle down in this positive steady state, because the zero solution is unstable according to this theory, right? On the other hand, if you are in the left-hand side of this E1, and if your initial population is too small, your population will die down in the long run. But if your population is above this particular threshold, above this lower branch of the red curve, your population will grow in the long run, and it will be settled into this upper steady state because that's a stable branch. Okay, we can of course show that this is an unstable branch. This lower branch is unstable. The upper branch is stable. Okay, that can be proven using linear stability arguments. And as you can see, if your habitat size is in this Allee effect region, dynamics are going to be interesting. Okay, you need to watch out. You need to make sure that your population size is above a certain threshold. Otherwise, you will lose your population. On the other hand, if your population size is smaller than this number, this leftmost point on the bifurcation diagram, then doesn't matter how large your initial population is, your population is going to collapse in the long run. Because see, here the zero solution is stable, right? Zero solution is stable in this entire region. But here, since the zero solution is stable and there is no any other positive steady states around, so your population will collapse. So that means if you need any chance of your population to survive in the long run, you need to make sure that your habitat size is bigger than this number, which is what typically we call it the minimum patch size. Okay, so if your patch size is bigger than that number, you have a chance for your population to survive in the long run. All right. As I mentioned, you can use this particular theorem to study not only these types of population dynamics models, even other types of models. For example, if your reaction term is increasing reaction term, those are kind of irrelevant to population dynamics models. You can even study those types of models using this particular theorem. Okay, so this is going to be a very interesting theorem. Um, Yeah, I think that's all I wanted to talk about. Here are some of the references that I used, and here is where you can find the derivation of the model that I talked about. The full derivation in this paper, the derivation is going to be a long derivation, so I skipped a lot of the steps. If someone is interested in, you can find the derivation in this particular paper. All right, thank you for listening. Yeah, someone has questions.
Uh, Thank you for a very interesting presentation.
Thank you.
Do you intend extending this modeling framework to predator-prey systems when the predators and preys could have different probabilities on the boundary of entering or leaving the domain?
That's a great question, actually. So still, I'm working with my advisor for on certain models, but I'm aware that my advisor's research team work on certain problems where you have different immigration probabilities on the boundary, and in particular, they studied the system where you have the logistic growth uh, for both species, the predator and prey, and they have different growth curves, and on the boundary they have different immigration probabilities. Yes, it has been studied in few of the papers, but I know that I'm aware that they are trying to do more investigations in that direction, but I have not studied any of the models that has this predator prey concept.
Thank you.
Yeah.
Guess I'll have another question for you. So I'm systems. If your domain was some kind of matrix with different pore sizes, do you think that you could use this modeling framework because when a chemical diffuses to the edge of the domain, there might be a probability of escaping depending upon the pore size at that particular part of the boundary?
Can you repeat that question? The initial part was cut off for some
Oh,
reason. I couldn't
yeah.
hear that clearly.
So I'm more interested in chemical systems, and I was wondering, suppose you've got a chemical reaction occurring inside some kind of porous material, and then there's a distribution of pore sizes on the boundary. Um, would that mean that the probability that you diffused out of the matrix it could depend upon the location? So do you think there might be a possibility of applying this kind of modeling framework to chemical systems?
That's a great question. I haven't thought about that yet, but there may be some connections because I have seen these types of models, in particular, these types of elliptic models, are used in chemical reactor theory, but I haven't done any studies in that direction. Uh, yeah, but my advisor has been involved in some of those projects. But for the time being, I don't have the details of such studies and how these concepts are translated to those chemical reactor theory.
All right, thank you.
Yeah, great question. I guess there are no other questions. All right, then I'm going to stop the meeting. Thank you so much for listening. Appreciate it.